Thank you, Mr. Chairman. My name is Ryoto Matsuzaki from Tokyo Denki University in Japan. Today, I will talk about study on compressive deformation of escalator truss during earthquakes concerning large deformation. In this presentation, this talk is as follows. First is background. Second is purpose. Third is experiment of escalator truss. Fourth is analytical result. Fifth is conclusion. Finally is the prospect of the future. This slide shows structure of escalator. In general, the escalator have truss structure that one end is fixed and the other end is not fixed. Non-fixed side is sliding during an earthquake and can suppress the transformation of the escalator. However, for accident of escalator utilized in three shopping centers occurred during Great East Japan earthquake in 2011. This figure is for photograph of escalator. After this accident, the quake resistance standard was revised in Japan. In new quake resistance standard, solid drift angle assumed during earthquakes was set larger than before. However, it is difficult to secure a sufficient clearance between the building beam and the escalator. And when the large solid drift angle occurs, the escalator truss may be greatly deformed by compression load and may cause trouble in safety. But it is difficult to do the full-size test with all escalators. Next, purpose. From the above-mentioned background, as part of building standard development promotion project in 2014, a compression experiment of the actual size escalator truss was carried out. The analytical model simulates the experiment. So the effectiveness of the analytical model is compared with the compression experiment of the escalator truss of the actual size. Last year, linear analysis was performed, but analytical model cannot reproduce the experiment. So this year, non-linear analysis considering buckling and unloading. In this paper, simple analytical model is created. First, considers welds steel as one unit, and second, properties of steel are set uniformly regardless of the shape of member. Next, experiment of escalator truss. This slide shows compression experiment of the escalator truss. In order to investigate the behavior of deformation due to the difference in the structure of escalator truss, experiment were conducted. And experiment compressed truss only. So the proof stress evaluation after deformation can be evaluated on the safe side because there is no deformation suppression effect by escalator's internal equipment. This slide shows test body. Weight of internal equipment is reproduced by hanging the dummy weight. This table is parameter of test body. This slide shows outline of experiment. Compression and unloading were given step by step, and the influence by repeated load was confirmed. Finally, enforced displacement was given up to 200 mm. This report deals with three patterns. This slide shows experimental result of pattern A. This figure is state of deformation of escalator. A large deformation at the lower end. This figure is a load displacement curve from experiment result. This slide shows pattern B. Pattern B is the middle part go down. Next is pattern C. Pattern C is a large deformation at the lower end. This slide shows experiment result. This figure is a comparison of 3 patterns. All trusses underwent elastic deformation along with an increase in displacement. After that, it buckled and the rod sharply decreased. There was no effect by repeated load. This slide shows conclusion. Even if displacement was given up to about 200 mm, all trusses were self-sustained without falling, and there was no rupture of the member. And there was difference in buckling load and transition of load. Next, analytical result. This slide shows analytical method of linear analysis. Analytical model is fixed the upper end and given enforced displacement of 5 mm. Analytical result shows the load displacement curve according to the load at which buckling occurred. This slide shows analytical result. Displaced on 50 times scale and deformation to sink down from lower end part to middle part. There was no local deformation. So the slope is different from the initial stage of deformation. Buckling cannot be reproduced by linear analysis. So in the linear analysis, deformation is subduction. So the buckling that occurred during the experiment cannot be reproduced. And the slope is different from initial stage of deformation. In the experiment results, the graph is inclined before buckling, so it is necessary to perform non-linear analysis. This slide shows non-linear analysis. A simple analytical model. Whereas steel as one unit, and property of steel are set uniformly regardless of the shape of member. Weight of internal equipment is reproduced by applying the load to the member. This slide shows analytical condition. Simulation 1 is yield cells of this standard, and simulation 2 is yield cells according to experimental result. Material property is bilinear model. This slide shows analytical method. Step 1, analytical model is fixed the upper end and given enforced displacement of 200 mm. Step 2, loading to 0 kN. This slide shows analytical result of pattern A. A large deformation from the lower end to the middle part occurred. This slide shows animation of analysis result. This slide shows load displacement curve of pattern A. The state of deformation, the shape of graph is almost reproduced. And a story drift angle of escalator during earthquake is determined by the quake resistance standard. When not obtained by structural calculation, it is necessary to consider 1/24th radian or more. Experiment and analysis was done up to 200 mm beyond that values. This slide shows analytical result of pattern B. A large deformation in the lower end occurred. This slide shows animation of analysis result. This slide shows load displacement curve of pattern B. Although the shape is different, the tendency of load reduction is similar. This slide shows pattern C. A large deformation in the lower end occurred. Pattern C's analysis result. Although the buckling load is different, the shape of the graph can be reproduced. This slide shows about vibration experiment. Vibration experiment of 3/10 scale model escalator truss was done. It will be explained in detail at the presentation tomorrow. In this study, static analysis was done beforehand. Reproduce collision with building beam due to earthquake. Confirm deformation due to dynamic compressive load. This slide shows analytical result of scale model. Static analysis is carried out, and it will be compared with dynamic deformation. Deformation that bends inward at the lower end was confirmed. Load displacement curve to the real escalator truss was obtained. This slide shows conclusion. The yield stress of the material used in the experiment is higher than the yield stress of the GIST standard. So in pattern A and B, the buckling load of analysis result using the GIST standard is smaller than the experiment result. But in pattern C, the buckling load of the analysis result according to the GIST standard is larger than experiment result. Pattern C might be influenced by the initial misalignment. And by matching the yield stress of the analytical model to experiment result, it is possible to reproduce the change of the load after buckling roughly. Next is conclusion. This slide shows a conclusion of experimental result. Even if displacement was given up to about 200 mm, all trusses were self-sustaining without falling. And the proof stress evaluation after deformation can be evaluated on the safe side, because there is no deformation suppression effect by escalator's internal equipment. This slide shows a conclusion of analytical result. In this study, a simple analytical model considered weld steel as one unit and the properties of steel are set uniformly regardless of the shape of member. Even with a simple analytical models, they can analyze considering buckling and unloading. It is considered that the analytical model can propose as things sufficient enough for safety margin evaluation of escalator truss in advance. Next, prospect on the future. This slide shows a prospect on the future. And to improve analytical model and check trend of analysis result, and to create analytical model with head height of 5 meter and 7 meter, and to compare deformation of compressive load with deformation of impact load from vibration experiment. Thank you for your attention.